All right, good morning, everyone. So today is the organic chemistry part that we're doing, the reactions of alkene. Now, very nice part of the work that we're actually doing. But just before we start, I would like us to just consider two of the terms, and that is an electrophile and a nucleophile. Right. So I'm just going to write that down here. Uh, electrophile and a nucleophile. Now, what are these? Why do we use such weird terms? Nucleophile. Well, electrophile refers to electron lover. Electron lover. So it is attracted, an electrophile is attracted to something that is negative. It has extra negative charges. So something, for instance, a carbon-carbon double bond. That's an electron dense area, and it opens it up for electrophiles to attack it. What is a nucleophile? And we'll deal with nucleophiles slightly later in organic chemistry, but just so that you know what a nucleophile is, well, nucleo and phile being lover, so it's nucleus lover. So something that has a positive charge, something that loves positive charges or are attracted to positive charges. Right? So the reason why I said this or start off with this, because the addition reactions of alkenes are all electrophilic addition reactions. And the reason for that is my double bond that we have there. So that comes under attack of electrophiles. Right. So the first reaction that we are going to look at is the electrophilic addition of halogens. Now, this is amazing what you've done in the IGCSE. You have alkene and it reacts with halogens, and it's a spontaneous reaction. Think about the reaction of where we test between alkanes and alkenes. Our alkenes react spontaneously with a halogen, like bromine water, decolorizing it and producing halogenoalkane. This is just a reaction with chlorine, for instance. What's the difference? My alkanes need UV light, right? So they need UV light to react for it. And that is to start the reaction by breaking my bond between my halogens. But here it is slightly different. That's just another reaction that I'm showing you. So the top one shows displayed formula. All the bonds are shown. The bottom one is in structural formula. Not all the bonds are shown. For instance, CH3, CH3 in there. Right? So just a little bit of awareness of all of that. Just a nice slide to show you the breaking of the bond, breaking of it, and attaching of it. Right. So with the electrophilic addition of alkenes, we need to look at the mechanism. So what we'll deal with and what is new for you guys in the AS part of this is to study the reaction mechanism. As I said, my double bond is an electron dense area. And because it's electron dense, as we have, if we have a bromine, and I'm just going to get my laser in here, my spotlight, as we get our bromine that is in close proximity, remember this is electron dense. This is a nonpolar covalent. As it gets closer to my double bond, it pushes this bonding electron pair actually slightly down, and it creates a dipole, a slight induced dipole, with slightly positive being attracted to my double bond and a slightly negative to my other side of my bromine molecule. And it's here that I just would like to bring in again the two different ways of bond breaking. Remember, we have a homolytic way homolytic fission. What is homolytic fission? It's where we have this non-polar bond, and with the addition of energy, so energy being in the UV light, for instance, it breaks up. And look at my arrows. It is curly arrows with half and half. And what does it produce? It produces a free radical plus a free radical. So homolytic meaning each one of the atoms gets a part of that shared electron. But in our example on the slide, we are dealing with the other one. We're dealing with heterolytic fission. What is heterolytic fission? Well, this is where we have, for instance, a hydrogen and a chloride. My chloride has a slight negative charge and a slight positive charge. And this is due to my difference in electronegativity. Now, what happens? My bonding electron pair is pulled closer to my chlorine. And when this bond breaks, due to whatever reason, the curly arrow indicates the movement of my electrons. So we're going to end up with a hydrogen that's positive plus a chlorine that's negative. Remember, there's my bonding electron pair. It's moved towards chlorine. Okay, so this is heterolytic fission. Hetero meaning different. The one gets all of it, the other one gets nothing. Homolytic, 1, 1. Okay, so what happens here? Because of the induced dipole, my bottom bromine that is now induced to be slightly negative will get my full share of the bonding electron pairs, producing a negative ion. So it breaks heterolytically and it produces, there we go, my negative bromide ion with my lone pair. My bromide that attacked my double bond is attached to one carbon and it produces a carbon cation on the other side. I'll elaborate now on carbocations. This is a primary carbocation. It's very unstable. Primary because it's attached to only one other carbon. This means my bromine will attack my carbocation, a negative and a positive, and we end up with our molecule. So this is known as an electrophilic addition reaction mechanism. Right? So very important. Let's quickly look at my stability of carbocations. You can see there is something written there, and let me elaborate and try and explain this slightly different. So if we have a carbon attached to only one other carbon, and I'm going to do that actually as a methyl group, and there's a hydrogen and a hydrogen on there, and that's a positive ion. This is a primary carbocation, right? So carbocation, cation referring to positive. When we have a carbon attached to two methyl groups, let's do it this way. There's CH3 and the CH3. The hydrogen is the positive. Two carbons, then it's called the secondary carbocation. If we have it attached to 3, then it's a tertiary. So 1, 2, 3 methyl groups to my carbon, then it's a tertiary carbocation. Now, what's the difference in here? My primary is the least stable because it's got an overwhelming positive charge to it. What do I mean? I mean that my alkyl groups, my methyl groups, has a positive inductive effect. It pushes that bonding electron pair closer to it, producing a slightly negative from its side, that being slightly positive. So it's sharing the electron bonding pair closer to my carbon cation. It's not enough to stabilize my positive ion. Remember, ions would like to react very fast. If I have two alkyl groups or methyl groups, for instance, remember this denotes, that little arrow denotes a dipole moment. This pushes two slight negative charges, the two bonding pairs towards it, more stable. Most stable carbocation is a tertiary carbocation, and it can actually exist as this carbocation because all three of my methyl groups has this positive inductive effect towards my carbon cation. It pushes the bonding electron pair closer to my carbocation, thereby stabilizing the ion. So this little slide shows it to you, and this one more or less explains it with my alkyl group, my methyl group, pushing that bonding electron pair closer to the carbocation. They call this a positive inductive effect. So go through it, look at it, and then with all of our reactions, we'll refer back to this because your primary one will react very fast. Secondary one is more stable, so reactivity is lower, and your tertiary, being more stable, has the lowest reactivity in there. Right? Remember, if something is more unstable, it will react faster. Let's look at our next type of reaction. This is called hydrogenation. Hydrogenation is the addition of hydrogen to an alkene. So very important in all of my reaction mechanisms is that we actually need to know the reaction conditions. So here we have a alkene that's dissolved in a polar solvent, nickel as a catalyst in an atmosphere of hydrogen at a relatively high temperature of 140 degrees. So what is hydrogenation? Well, it's the addition of hydrogen to a double bond, and we end with ethane. Very significant in industry because this is how they make margarine from sunflower oil. So a very important process. I think you would also know this from IGCSE. The next one is hydrohalogenation, and this is the one that I use as an example for the heterolytic fission, where we have a hydrogen and a fluoride for chloride or bromide, so a hydro referring to hydrogen and halogen towards the halogenation. So very important, this is that at room temperature, no water is present. Here we go, and room temperature. So very nice. I'm taking the easiest example again, an ethene plus my chlorine and hydrogen. Doesn't matter which hydrogen gets my chlorine and which one gets my chlorine. But as soon as there are more options, look at it. So we've got an option where when I have prop 1E, where my bromide can either go to my second carbon or where it attaches to my first carbon. Now, according to this guy, Markovnikov's rule, my bromine would attach to my carbon with the least number of hydrogens. Can you imagine why? Well, look at it. It's a secondary carbon. So my hydrogen will attach very quickly to my primary carbon over there, and then my bromine will attach to my secondary carbon. This is all to do with the energetics of bond strength as well. Now, we haven't done bond strength, but my hydrogen has a lower bond strength than my bromine. So it would like to attach fast and will go to the more unstable carbon in there, right? While my bromine goes to the more stable. So both of these products will be present in a solution, a product in the end. But the one is a major product and the other one is referred to as a minor product. Just by reference of the availability, it would be more of this and less of this available. Okay? So you don't need to know Markovnikov's rule by heart, the rule. You must know how to apply it and get to the major product. Oops, going to that. I hope that is clear enough. My very important reaction of oxidation. Now, oxidation we can define in two ways. We can say, listen, oxidation is the transfer of electrons. So just quickly, oxidation is the loss of electrons, while reduction is the gain of electrons. Remember from electrochemistry, you've done that, right? In organic chemistry, we can view it in a different way. Oxidation is gain of oxidants, right? Or we can say oxidation is the loss of hydrogens. So it's a different way of viewing oxidation. Reduction is just going to be the opposite. Reduction is going to be the gain of hydrogens and the loss of oxygen. So this is important. Look at what happens. And there's two very important reactions regarding oxidation with alkenes. The first one is where we add cold, diluted, acidified permanganate or manganate. So this is how that looks like when we write permanganate, and H plus refers to the acidified. In this reaction, there's water involved in there, right? Because we say it's dilute. If something is dilute, there's water with it. Now, luckily for our syllabus, AS and A level, we do not need to use that. They simplify it by using an O. Why is that? Because remember, whatever you add with your reactants must be present in the products. And the formation of molecules with your potassium and manganate on the other side, it's really complex, right? Because it's not just a manganese and a potassium forming, there's a manganese dioxide and so forth that forms on the other side. We don't want to go into that. So for oxidation, we use our oxygen in square brackets, must be square brackets. So what happens? When it's cold diluted, my double bond breaks and I add hydroxide and a hydroxide to each one. And we refer to this as a diol that forms. So diol, alcohol with two alcohol groups, right? So whenever it's cold diluted, acidified permanganate, diol forms. Easy. Very important. When we use hot concentrated permanganate, right? So again, hot and concentrated. Now it's not just one bond in the double bond that breaks. We break that total one because it's hot and it's concentrated. It's got a lot of permanganate. We've got extra energy and it breaks right and off. So here we have the molecule 2,3-dimethylbutene reacting with a hot concentrated solution of permanganate. And it forms two ketones, a prop-2-one and a prop-2-one. Question now, can we oxidize this carbon more? That means, is there a hydrogen that we can lose to gain an oxygen? On this specific carbon? No, there isn't. So this is the final product. Because I've asked this, obviously there are other options as well. So look at this. If we have a 2-methyl butene, again, hot concentrated permanganate is added. We break our double bond. We add our oxygen to it. We end up with a ketone. No hydrogen to remove, no oxygen can be added. Done with this. What is that? That's a hydrogen. Can we remove that hydrogen and add an oxygen? Yes, we can. What's the difference? This is a ketone. This is an aldehyde. An aldehyde can be further oxidized, right? But a ketone cannot be further oxidized. If you can remember that, my lesson is done, done and dusted, sorted for the next 2 weeks almost for organic chemistry. Okay. Remember, concentrated means a lot of that specific molecule. Right? It's not diluted, there's a lot of it. So we can oxidize further. So in essence, we can oxidize an aldehyde further to carboxylic acid. We cannot oxidize a ketone further. This is going to be very important when we start testing different solutions for which molecules they contain. So please remember that. Let's go through a little bit of a summary. And I need you to see the following. If we have, for instance, the molecule on the page there, what is that? That is a 2-methyl propene, 2-methyl-propene. Let's do this. We have a C and a hydrogen and a hydrogen. We have my double bond, carbon, we have a methyl group, we have a methyl group in there. All right, let's add my oxygen, my permanganate. And you'll see there. All right, okay. So if we have that oxidation, yes, we know this is concentrated. We know it's hot. I'm just giving a little bit of a clue there. So we're going to have 2 products. What is happening? We're breaking the double bond. We're adding oxygens. It is oxidation. So this is my first product with my double bond. And my carbon, CH3, CH3. And we have a ketone in there, 1,2-one or propanone, right? That's fine. But there's a second product that forms on this side. What is that second product? Well, we have a double bond oxygen, carbon, and now we have a hydrogen and a hydrogen. So according to our definition for oxidation, remember this is concentrated, there's a lot of my oxygen, my permanganate in there that can oxidize a molecule. Can we remove a hydrogen and replace it with a hydrogen, with oxygen? Yes, we can. How is that going to look like? So now we draw our oxygen, we have our double bond carbon, and now it's oxidized to that. And this is a carboxylic acid, right? The most simplest one, methanoic acid. Can this be further oxidized? There's still a hydrogen in there. Yes, it can be further oxidized. Look at this. Just giving myself a bit of space. It can be further oxidized. So what do we have? Well, we have our oxygen, double bond, carbon, double bond. What does that give me? This is nothing else than carbon dioxide. Just look at this. This is a hydrogen and a hydrogen, and there's oxygen available, and we get this. So if we have a primary hydrocarbon attached to two hydrogens, it will be fully oxidized to carbon dioxide and water. This is my first point there. Primary carbon attached to two hydrogens are oxidized fully to carbon dioxide and water. Very important. This is a normal combustion reaction. Combustion is oxidation. Secondary carbons that has two carbons attached to it and one hydrogen are oxidized to an aldehyde, and an aldehyde can be further oxidized to a carboxylic acid. My tertiary carbons are only oxidized to ketones. This is nice. This is the most important slide that you will have. This comes into play when we do alcohols, when we do ketones, when we do all ketones and aldehydes, alcohols, and carboxylic acid. So very important to know how they are oxidized. I know our starting point was alkenes, but remember, we're going to do mechanisms and a whole lot of these reactions. Okay. Addition reaction with hydration. So what is hydration? This is easy. Hydration is where we add water to it. So there's my reaction. Water is added to it. Remember, our conditions, high temperature, high pressure, and a strong acid. It could be sulfuric acid as well. There's our reaction. I did the simplest molecule for you. Doesn't matter where the OH comes, it's going to be on the first carbon. But when there's more than one option, remember Markovnikov's rule, it's going to go to the secondary carbon for stability. That is Markovnikov's rule. It's going to go to your secondary carbon, major product. It's on my first carbon, it's my minor product. Question papers can ask both. Right? The last reaction that I would like to do with you is elimination. So this is the opposite of hydration, and we call it dehydration. This is important. Note temperature, 170 degrees, sulfuric acid. So this is when we have an acid catalyzed reaction. The hydrogen and OH is removed, and the way that it's removed follows Zaitsek's rule. That the carbon with the least number of hydrogen atoms will lose a hydrogen in the formation of it. So one with the least number, so the most, will carbon with the least number of hydrogens will lose a hydrogen in the formation of a double bond, right? So we'll look at that in a bit more detail. The next bit, I would like you to read through addition polymerization. I'm going to give you homework on that. Read through it, look through it. It's something that you've also done in IGCSE. We don't continue into more detail though. It is the essence, the basics thereof is that. Okay. What is important? It's important that you guys practice these reactions. The reactions and reaction mechanisms from here requires a lot of studying to know the detail, knowing the reaction conditions and knowing the products that form. Right? Please, please, please go through that. I'm giving you homework. You will see that on the WhatsApp group, and then that is for Thursday. Thursday we'll continue with the last bit of this lesson and we'll mark our homework. Okay? Hope you enjoyed it. Keep well. I hope to see you very soon in class.